Now let's take a look at example number 4, which says factor each binomial if possible. There are situations where binomials or polynomials in general cannot be factored, in which case we would not have an answer. We would just say it's a prime polynomial. Now, as you can see in all of these problems that we're about to do, example 4 has basically 2 terms in the first one, 2 terms in the second one, 2 terms in the third one, and so on and so forth. Now, if you look at 9 and 16, there's nothing common there. So for instance, 9 is 3 times 3, whereas the 16 is 4 times 4, and nothing repeats. Similarly, the 4 is 2 times 2, and the 81 is, for example, 9 times 9. Nothing is repeating there either. So it turns out that for this problem, we use a different strategy compared to the one we just did in example 3. So we're not going to use the Gcf method because nothing is repeating. So what we have to do is pay attention to the special formulas technique. So in the special formulas technique, basically you're given patterns. Some of these patterns are called difference of squares, sum of cubes, difference of cubes. And you're supposed to use them to factor polynomials. So first things first, the difference of squares. This is a common one. It's the formula number 2 in this list. Basically tells you if you have 2 terms that can be written as perfect squares, then you can turn it into a product of the first term minus the second term multiplied by the first term plus the second term. So this is known as the difference of squares formulas. If you hear that, that's what we're talking about. Now, the summation, though, on the other hand, cannot be factored. So if you have 2 terms that are perfectly squared but with a plus in the middle, that cannot be factored. So let's practice that technique with example number 4. So we have 9x squared minus 16, and instead of breaking it down like we did in example number 3 as 3 times x times x minus 4 times 4, it's not very helpful to do it that way. Instead, what we notice here is that the 9x squared can actually be written down as 3x all to the power of 2. So actually, I can rewrite the 9x squared as something that is raised to the power of 2. So that's great. And I could do the same thing again with the 16. I can write down the 16 as 4 to the power of 2. So that is awesome. We can rewrite it. So I'm noticing that there's one term raised to the power of 2 minus a second term raised to the power of 2. So what does that mean? That means that I can use the difference of squares formula. So the formula says if you have a squared minus b squared, then it's going to be a minus b multiplied by a plus b. And in my situation, in my case, the a is actually 3x, and the b in this case is going to be 4. So all I have to do is write down 3x minus 4, and then 3x plus 4, and I'm basically done with the problem. So again, you take the base that was first, and you write it down a couple times. You write the second base, which was 4 in this case, a couple of times, and one time you put a plus, one time you put a minus. The order here does not matter. You can put the minus 1 first or the plus 1 first. It doesn't really matter because it is a product at the end no matter what, so it's not going to make any difference. So that's what we call the difference of squares pattern. Now keep in mind that this only works if you have a minus in the middle of the problem. If you don't have a minus there, then this is not going to work. So if I try to do the same strategy again with part 2 of this problem, I can rewrite the 4x squared as 2x all to the power of 2. I can write down the 81 as 9y to the power of 2. So then 81y squared can be rewritten. However, unfortunately in this case, we have a plus sign. So this is kind of bad. It just means that this problem cannot be factored. So when something cannot be factored, we just write down the word prime. Prime means it cannot be factored. As a matter of fact, the answer to this question is the original thing that we started with, the 4x squared plus 81y squared. Cannot be factored, so that's the end basically. So sometimes we use the word prime to refer to these kinds of problems where no solution exists. The last example on this page says 25x squared minus 16y squared, and so in that case, again, we can rewrite the 25x squared as 5x all to the power of 2. We could do the same thing with the 16y squared and rewrite it as 4y all to the power of 2. Now, some folks can skip this step. They can do it mentally, which is great. It's awesome. But if you can't do it mentally, you could just write down what I just did and make a record for what the a is, what the b is. And again, write down the 5x, the 4y a couple of times. One time put a plus in the middle, one time put a minus, and that's pretty much the end of the question. So again, the first base goes in the first parentheses and the second parentheses. The second base goes inside, again, the first parentheses and the second parentheses. And one time you put a minus, one time you put a plus in the middle, and that's it. You're basically finished. So this pattern is what we call the pattern of difference of squares. This pattern works when you have two terms that have a minus in the middle. Now, if you look at the next few examples, the powers are 3. So in that case, we use a different formula. The formula actually is in the same table that I just showed you. It's actually one of these two. We call these ones the cube formulas. One of them is the difference of cubes, and one of them is the sum of cubes. They have a similar pattern, so I'll describe it in an example. So starting with the first one. Now, if you carefully look at this guy, it says 2x to the power of 6 plus 128 y to the power of 3. First of all, the 2 itself is not a cube of anything, at least not anything nice. Same with the 128. It's not the cube of anything particularly nice. But 2 and 128 have repeating factors. For example, 2 is 2 times 1. And the 128 is the same thing as 2 times 64. So I'm starting to mix and match the methods with one another. In this case, I'm going to go with the Gcf method. Remember, we said we always try that first. Take out whatever common factors you've got, and then leave the leftovers alone. So in this case, the leftovers are x to the power of 6 and 64 y to the power of 3. Now, this would be factored, but it's not factored completely. So I'm going to continue and break the numbers down even more so I can factor them some more. So the 2 that I factored, which was a GCF, gets written in front, and once it's written in front, I just have to keep carrying it over and over again to the next few lines. Now, inside the little bracket, what's going on there? So looking at the second term, I'm seeing y to the power of 3, and that's the indication that I need to use the cube formulas. So what I have to do now is think of a way to rewrite the first term, x to the power of 6, as something to the power of 3. And I have to think of a way to write down the 64y cubed as something to the power of 3 as well. So what's the base that you can raise to the power of 3 to get x to the power of 6? Turns out that the base is x to the power of 2. This is from the exponent rules that we learned. 2 times 3 would be 6. That's the x6 that was there. So that's great. The plus sign that was in the middle stays in the middle. And then finally, what do you cube to get 64y cubed at the end? Well, the solution is 4y. So turns out that we have to use the sum of cube formulas. We have a plus and we have two different cubes. Now, what does the formula say about sum of cubes? It says when you have a cube plus b cubed, it's going to be a product of a small parentheses with a larger parentheses. In the first parentheses, we put the bases a and b. In the second parentheses, we put the base a, but squared at the beginning, and then the base b squared at the very end. And in the middle, we multiply the two bases a and b with one another. Now we need to put some pluses and some minuses. So there's a pattern. If there's a plus in front, we put a plus inside the first parentheses. So it's always going to be the same. Next, if you just put a plus, the next one is going to be the opposite, the minus. So in this case, it's the opposite. And then finally, at the end, the last term we put is always positive. Some people use an acronym to remember this. The acronym is SOAP. Same, opposite, always positive. So for me, what would that look like? So first of all, there's the 2 that I have to carry. There's going to be a tiny little parentheses followed by a significantly larger parentheses. And again, the way it's going to work is the first base goes inside the parentheses, x squared, and then the second base goes inside the first parentheses. So we just copy the original bases, kind of like what we did in the previous examples on the previous page. So at this point, in the second parentheses, what we do is we square the x squared to get x to the power of 4. That goes first. Then we square the 4y and we put it at the end. 4y to the power of 2 is going to be at the end 16y squared. And then finally, to finish this up, we multiply the two bases together. So 4x squared y, put that in the middle, and you're basically done with the setup. All you have to do now is put some pluses and some minuses. So how does it work? Earlier in the problem, we had a plus sign, so we put the same inside the first parentheses, then the opposite, then always positive. And that's the factored version of the problem. That's the final answer. Now, pause the video and see if you can try to do the same on the next example. You're going to have to do some sort of factoring like I did with the Gcf method. Then you're going to have to use the formula that I just gave you, but instead of a plus, you're using it with a minus sign. But the same rules apply. So pause the video here and attempt to do the next problem. So in this case, I did a step mentally at the very start. 16 is the same thing as 2 times 8, and 250 is the same thing as 2 times 125. The 2 is repeating, that's why you're seeing a 2 in front, and that keeps carrying from one line to one another. Okay, so that's the start, and 8x cubed turns out to be the same thing as 2x to the power of 3. The 125y cubed turns out to be the same thing as 5y all to the power of 3. And I'm using the same SOAP business that we did on the previous example with the bases 2x and 5y.